hopefully some slides are going to come up in a second. So I'm Suzanne Aigrain. I'm a lecturer in astrophysics at the University of Oxford, and I look for and study extrasolar planets, which are planets around other stars than the Sun. What I really want to do with that, so it would be helpful if my slides could come up. But what I really want to do today is to impress upon you the fact that we live in a very special time in a way that's slightly different to what Seth just said. We live at a very special time because 20 years ago we knew of no other bodies around other stars like the one that we live on. There were no planets known outside the solar system. Now we know of several thousand. We know that they are extremely common. We are very close to being able to say with a good degree of certainty that planets like the Earth, what we would call habitable planets, are also quite common. And so that's why when Seth asks whether I believe there's life on other planets, I raise my hand, and I do so as a scientist because the balance of probability, I think, is overwhelmingly high. And I feel immensely privileged to be here at a time when I can actively study these bodies and map their extreme diversity. One of the big surprises of the past 20 years is that many of the planets we're finding are nothing like the Earth, or in fact nothing like the planets that we know of in the solar system. And we're actually also able to start observing directly their atmospheres and learning about what the conditions might be inside the atmospheres of these planets, or for the ones that have a surface, on their surface. And I'm part of study groups that are actively thinking about what sort of technology we need to go and look for life on other planets around other stars than the Sun. The methods that we've been using so far to look for planets around other stars are indirect, because astronomers use light electromagnetic radiation as their primary tool to study the universe. We can't go and make our experiments, but exoplanets, planets in general, typically emit no light of their own or very little. So we typically have to look for planets indirectly through the effect that they have on their star. And despite this indirectness, our methods have been staggeringly successful at discovering exoplanets. The first few that were discovered were giant planets like Jupiter, but orbiting very close to their stars. That happened in the early to mid-90s, and ever since we've been pushing the boundaries. One of the most successful methods in the last 5 to 3 years has been a method called the transit method, which is the one that I work on, which consists in looking for a small dip that occurs whenever a planet passes in front of its star. And this dip repeats every time the planet orbits its star. And one of the missions that has brought this to the forefront of the media recently is the Kepler mission, a NASA space mission. But before that, there have been European ground-based and space missions that have also made great inroads into the question of how common are exoplanets of different types, and in particular habitable exoplanets. So I'm going to spend just a couple of minutes talking about what I mean by a habitable planet, because I think that's a very important concept, and it will highlight a big problem that we have when we want to look for life on other planets. When we talk about habitable planets in the astronomy field, what we really mean is actually a planet that's roughly the size of the Earth, and where the surface temperature, which is governed by how much light the planet receives from the star and how much greenhouse effect there is in the atmosphere of the planet. So where that surface temperature is suitable for liquid water to exist on the surface. Why do we make those choices? Well, we think that on the Earth, water was the solvent in which the first organic molecules assembled themselves and in which the first life appeared. And so we don't necessarily know that this is the only conditions in which things can happen, but it's a good place to start looking. And similarly, we also think that plate tectonics played an important role in allowing life to survive on the Earth, certainly. For example, you may have heard of so-called snowball Earth episodes that happened in the distant geological past on the Earth, and we think that volcanism played an enormous role in essentially kicking us out of these snowball Earth episodes by injecting lots of carbon dioxide into the atmosphere. There are other reasons also why we think that volcanism is very important. And volcanism, essentially, for a planet to sustain plate tectonics over a long period of time requires a certain minimum size. There's a maximum size as well, because if a planet gets too big, it starts to accrete an envelope of gas like Jupiter, and then the conditions become so different from the ones that we have on Earth that we can't really conceive of a form of life that would evolve in these situations. But these are very, very human-centric ways of looking at things. So we also have to bear in mind that life, if it is out there, could consist of something completely different to what we are thinking of. Once we have planets that we think are suitable for life to evolve on, we may then ask, well, is there life out there? And the life markers, the biomarkers that we'll be looking for, as Seth said, are trace gases in the atmospheres of these exoplanets that we think can only be there if they are being produced by a biological source like photosynthesis. If you take a spectrum of the Earth from space, so if you disperse the light that the Earth emits or reflects along the different colors, you will see some very key signatures of molecules like water vapor, carbon dioxide, and most importantly, ozone and molecular oxygen. Oxygen and ozone are very reactive molecules. If they are present in large concentrations, it means that they must be being produced. So this is essentially the principal biomarker that we are designing future missions to search for. And we think that we will need large space telescopes ultimately. So things which are the size of the currently biggest telescopes on the ground, 8 to 10 meters, but in space, to be able to look for biosignatures on the atmospheres of these planets. And I think I'll leave it there, because that covers mostly what I wanted to say.
Yeah, there were mutterings that they're being able to pop up slides on that. That seems to have not occurred. I think that may also be a problem that you That's grand. Okay, well, we'll put out a proper call for that to occur. Do you want to take a minute and then we'll carry on with this discussion, then you wait, or would you like to talk now? Do you want to give it?
I will go on and start. Can mission control? Mission control, Houston, we have a problem.
This really cannot be the worst problem. This cannot be the worst problem that someone in your job has ever had to face.
I've already taken care of it. Thank
very
you.
Good. Congratulations.
I've taken care of it.
Tell you, walk one step away and I'll introduce you, and you can do the big walk on. So, ladies and gentlemen, our final speaker joining this panel has been a chemical engineer, has been a dancer, has been a medical doctor, has been a choreographer as well. Any one of which would have been a fine reason to talk to her. But in 1992 spent 8 days on board Endeavour. Ladies and gentlemen, would you please welcome, previously of NASA and now very interested in the field of innovation as well as interplanetary travel, Dr. Mae